Hello, this is Jeffrey Fox, Introduction to Cloud Computing and Big Data / Data Engineering. Part J is software, cloud software. And let's get on with it. This section is close to my research heart. We go through what we introduced here, high performance computing enhanced, Apache Big Data stack, which we have 350 packages of January 2016. And they're divided into 21 layers, and we describe each of those layers. So very briefly, we note that Google is a pioneer. MapReduce can be pictorially represented. We compare cloud and HPC software stacks, and we go through the components needed to support cloud and distributed systems programming, which we get by reverse engineering the existing systems. The last slide is a discussion of SPMD, single program multiple data, mentioning single instruction multiple in data, which is an old-fashioned parallel computing approach. All right, now we have the famous HPC-ABDS, high performance computing enhanced Apache Big Data stack, with the 350 software systems that I gave up updating in January of 2016. So in here you also see there are actually 21 layers. They're numbered from 1 to 17, but 4 of them have, or three of them have A, B, or ABC divisions. The 14 and 15 are A and B, 11 are ABC, showing I didn't quite do the layers correct. So I sliced up the software stack. The ones on the right here are cross-cutting. Like security is not really a layer, it's runs through everything. As is messaging, it runs through everything, or message protocols do. And here we basically start from the bottom, that's infrastructure. And then right at the top with workflow / orchestration, which is how to join multiple jobs together. And in between them, we build a job with some data, some messaging, some programming systems, libraries, and so on. Here we're managing the cluster, the file systems, the actual resource management, and we have various standards for interoperability, and we have DevOps, which is automating the infrastructure. So this is not all Apache Big Data. There are some commercial products here. There's some non-Apache open source like MongoDB. There's some commercial products, but they all come from the same community and represent the state-of-the-art in big data systems. And around January 2016, we were kept on updating it every month for several years. I decided we had enough, and the picture was clear. I was no longer getting any new information in my update. So the other comment on this, some of these are green. Green are the layers we happen to work on in a big NSF project I have, 14-43054. Those are where we researchers in academia focus. Okay, now as a backdrop to this is actually what Google does. So Google is, of course, the pioneer, or probably the original pioneer, and now a very competitive pioneer in the field, and it keeps on doing wonderful software. And here we have a sort of history, which Google likes to show on in this slide here. And I've written it out here because you can see it more clearly. Starting with the Google file system, which is shown here, then the most famous, probably MapReduce, and going on to Cloud Data Flow, which 2015, and then we've written the equivalent Apache technology where it exists. Now we've also written the layers. See, these like level 8 is the layer or level of the HPC-ABDS. Some of the capabilities we don't have in here because maybe Google hasn't openly written a seminal conference paper or journal paper. Security, data transfer, scheduling, DevOps, Although Kubernetes is DevOps, which is from Google, but it's not really all of DevOps. It's just a very particular DevOps technology. And then we have serverless computing, where Google offers it on Google Compute Engine, but they don't have anything like a revolutionary paper, which say, partly because they didn't invent this. This came from Amazon with Lambda. I don't even think Amazon had a revolutionary paper. This is now Apache OpenWhisk serverless computing, but Google didn't contribute that. But anyway, they've actually contributed in the majority of these layers, and they typically were the first. Bigtable was the first NoSQL database and things like that. Prego was one of the very first iterative MapReduces, where we were actually somewhat before Prego, because that's not surprising. Academia does these things out there. All right, here is an example coming from Judy Chu, who taught cloud computing for many years with great success, and here's an illustration of its operation. So you have a program which has input data, which is split into parts, one per processor, or one per process, or thread, and those go to workers. And these workers are on the map side. The map actually do the work, and the reduce side. The reduce add up the work of the workers. Sorry, of the maps. And they each run on they can run on the same computers or different computers. But there are these two stages, and they're linked by writing to disk on your local disk. That is why you has, for instance, in the Hadoop, which is the Yahoo and now open source implementation of MapReduce. It has HDFS, is actually possibly the most famous part of Hadoop, which is the Hadoop file system, which allows you to have disks on the nodes with the maps running, being used to dump the data. And then the final answer, which, a typical reduce is a rather generalized reduce. It's not what actually some fields would call even reduce. They might call it a gather. And a typical example is search. The map is diligently searching for what it wants among the split up data, and the reduce does a sort on the reduce to sort the results in the order of most relevance. But it joins the results of the maps together. That's the so-called reduction. It's actually an increase operation, not a reduce operation. This slide here is sort of standard slide I've used in many forms for several years. On this side here, the left, it has the big data stack, and on the right, it has what you might call a classic cluster stack. And it has these different layers. Doesn't quite have all the layers, because some of them we don't particularly highlight in these when thinking about these stacks. We don't actually have DevOps here, even though we're going to use DevOps. So we start at the bottom with infrastructure, which, as I said, is going to be Docker or serverless these days for big data. And on the right is basically Linux or bare metal, and SRIOV is a technology to allow OpenStack to run very fast on supercomputers. Data management might be HBase for the big data case, and it might be iRods, a wonderful metadata management system for files, which we don't tend to use in the big data side on the cluster side. Here we have streaming data done with Heron on the big data side, but nothing on the cluster side, because there is no standard for doing streaming. Parallel runtime Hadoop with possibly our extension Harp or Spark. And then on the cluster side, you have MPI, OpenMP, CUDA, etc. And there's lots of runtime being built for exascale machines. High-level programming is Pig or Hive or Drill. From the big data side, it's the main Pacific languages on the cluster side. I had the nerve to put Twisted 2 as platform as a service. That's our own system. But there is endless, if you just look at level 15B, you'll find lots and lots of examples in the big data space. Orchestration is Google Cloud Dataflow up here, which is Apache Beam. And then on the cluster side, you have Kepler, Pegasus, Taverna. Libraries, here I put our own Spider big data library, TensorFlow. Python has lots and lots of libraries. And libraries are very important in the HPC side, when I've given here some classic libraries, Matrix, Sparse Matrix, and the many libraries MATLAB has. Languages are also a little different. C, C++, Python, and Fortran. And on the big data case, Python is shared, but you would also use C and C++, especially if you're Google. But language like Java, Erlang, Scala, SQL, of course, and Sparkle for querying graph databases. Coordination, there is nothing on the cluster side. Zookeeper for the Apache side that allows you to do distributed coordination. Caching also is not highlighted in the cluster side. And Memcache is a very famous in-memory caching system for databases. Data transfer, well, it's not so clear how you do that on the Apache side. Publish subscribe is used for streaming data. You could, in principle, use Globus on both sides, because it's basically grid FTP, and FTP is FTP, a famous technology. Scheduling, we have these interesting comparisons, Yarn, Mesos on the data side compared to Slurm, which is the standard scheduler, which is a little lower level than Yarn and Mesos on the big data side. My guess is something like Mesos or Yarn will actually become the standard scheduling system, and Slurm will get integrated into it. Slurm is really not good at interactive jobs. It's mainly for batch jobs. File systems, I already discussed HDFS. Object stores are things like Amazon S3, very common in big data systems. Lustre, which is a shared file system. Notice these are, here we have HDFS, which is a low-level file system with the long-term storage of object stores. In the classic cluster, everything is files. And then we have lots of formats. HDF is a standard format in the scientific computing. FITS is one, I think, in astronomy. All right, so they actually have similar structure, but rather different entries because they're optimized in different ways and have different histories. So now we finish those detailed discussions, and we stress just one thing, that when we talk about clouds, and this is relevant for this whole section, clouds have infrastructure. Usually people initially focus in defining clouds on the infrastructure as a service side, with the, that's how it was initially presented. Rent services, elastic services. But cloud is also notable because of the way it was set up. It spurred this amazing software activity, which was never seen before. At least I don't remember such an amazing coordinated software activity done by the community. And the community was just very big because there were so many large companies. The previous communities, like when web services were created, that community was much smaller than the community that created big data software. And that's actually sort of interesting. It might be worth studying why the communities have different sizes. All right, so here is a rather technical 2 slides, which I don't recommend going to any detail. They basically reflect the reverse engineering that we did on the programming models, which have some runtime which supports the processing of big data. And we divided them up into areas. For example, we have so-called coordination points. That's because typically these runtime support data flow, and data flow has something going from point A to point B to point C, and they do some linkage at these points. So those are coordination points. That's where you can change what's happening. That's where you can do backups. Very important. Spark, for example, is well known for its RDD backup system or caching system, and that happens at coordination points. It's not present in, say, MPI or other classic runtimes. You have to actually map whatever resources you have, whatever computers you have, to the maps in Hadoop or the tasks in Spark and in the bolts, which are the equivalent of maps in Heron and Storm. And that you have to decide whether you're going to use containers, processes, or threads. Then we have parallel computing, and we have these entries here: Spark, Flink, Hadoop, Pragal, MPI. They all have different modes, and they all are different modes, and they reflect parallel computing being universal, but being implemented in different ways. When we discuss parallel computing, we should note, although I don't think the slides do, the owner computes rule, which is reflected in most of these modes, which says if you're a computer and you're in charge of data points X, Y, and Z, you calculate whatever's connected to X, Y, and Z. So the owner compute rule says where the data stored is where the computing is. And there's a reason for that. You don't want to transmit the data because communicating data costs time. So you try to do the computing where the data is. That's a very important principle. We have job submission. And then we just have here various job submission technologies: Slurm, Yarn, Mesos, Marathon, Aurora. The last four are all Apache type job submission technologies. And then you're going to go take Python and actually have your client API be Python, and it can invoke these plugins. A typical architecture is to have the user sitting on a client running some powerful system, MATLAB, let's say it's Python. And that Python is not actually doing the computing, it's invoking the computing. So it's a proxy to the computing. It's a very important idea. People think some things are very inefficient. They're not inefficient because these slow technologies like Python are not used to do the job. They're the logic that invokes the job. If we now look at the tasks, we have to migrate tasks. We monitor them, see when they're busy, see when they need to be moved off a busy core and put on a non-busy core, or busy node and a non-busy node. Elasticity, which is certainly seen in OpenWhisk, is a key technology. Streaming and function as a service. Those involve events. Those events have to be processed with technology like Kafka or RabbitMQ. And then they're handed to OpenWhisk or Heron. OpenWhisk is function as a service, Heron is streaming. We have to study the task execution, whether we do process on threads, we'll have queues of work. Scheduling, we have to schedule the work. And this Spark, for instance, does dynamic scheduling, Flink does static scheduling, and then generally you want all types of scheduling. So you need to be able to choose and plug in different scheduling algorithms. You also have to support accelerators. Sometimes your work is done on your Intel or AMD node, sometimes on an accelerator from NVIDIA or Intel, like where it's CUDA is the software for NVIDIA, and Nice Landing with Intel's DAAL is an Intel accelerator. Now, all of these things are specified by a graph, and you need to be able to process that graph. So that's an important part of this runtime. All right, next slide. This is the last slide on runtime. Well, we have messages. I told you the world is full of messages. And Heron is built. Heron tells you how to implement messages. I pointed out that that's when you're coming from the edge to the center. Those edge systems communicate with the center of our messages. Data flow. Well, your system probably running in the center actually can run in a distributed fashion. Flows data from one thing to another, and that is done. We have our own system here, but there's also many ways of doing that, and we're exploring that. And there is also, one has to look at fine grain, where the data is flowing in small sizes, and coarse grain. And in some other talks I give, I distinguish between fine grain and coarse grain because they get mixed up in some of these systems. Here we have a comment on communication. Bulk synchronous processing is a style of communication typically implemented in MPI or our own system from GD2 called HARP. And their MPI is probably the fastest. Data. Well, we better know what data system we're doing, NoSQL, SQL, object stores, file systems, what have you. Then we also have to have streaming data. That's batch data, there are many choices. Streaming data gives us other choices. Data management. Well, we have to worry about data being immutable. When you're doing a typical Hadoop job, the original data is immutable. You're not touching it. But there's mutable data, which is the results of the Hadoop run. And we have to know how to deal with this data, especially when it's distributed and possibly inconsistent between the different nodes. And here, Spark with RDD and Heron with Streamlit has some technologies. Checkpointing. Well, you can decide where you want a checkpoint. And Spark and Flink and MPI and Heron all have checkpointing models. And they're different between batch and streaming. And we have to worry a little about some of these technologies are better at streaming than others. Heron and Flink are pretty good at streaming. Spark is not. MPI is dreadful. And then there's security. And I'm not an expert in security, except I know it's needed. And it's needed at the messaging level, the execution level, and the storage level. And it sort of crosses sort of everything. So this is when you sort of worry about building these systems, these are the things you worry about. Right, the next few slides just go through the 21 layers one after another. Layer 1, these are the cross-cutting layers. 1 through 3 were cross-cutting. This is message protocols. You probably won't worry about that in your work. There are these standards which are being produced to define the protocol for messages. I mentioned actually the Great Web Service hullabaloo, which is a really most complicated protocol. Distributed coordination. Well, this is a classic subject of the distributed computing course in computer science. Zookeeper in Apache is a famous implementation of some of the standard ways of doing distributed coordination, and there are various improvements of that and get better performance. Many Apache systems just invoke Zookeeper to do their coordination. And this basically it all comes from the fact that when you're doing parallel or distributed computing, you need to have some consistency because you have different jobs sitting there running, and they better have the same view of the world, or if their view is different, you better know it could be different and adjust to it. That's what Zookeeper goes with, keeping distributed systems on the same page. And if they're not consistent, appropriately worry about it. And the security and privacy is in a huge area. Lots and lots of people work about it. You see it on the web, and mistakes are always being made by big and small companies, and we'll always have emergencies. We have to go and worry about our own computer with things like that. And there's all sorts of technologies which try to, and then there's sort of trouble about security and privacy. It conflicts with user convenience, and we have various technologies here, like InCommon is one technology mentioned, which is a way of federating logins so that you can have a login at Indiana University and use it in other places, like the National Science Foundation. In future systems, we use Ldap, which is a very simple database, which basically holds all the information, which allows you to implement a security system because you store the details of the allowed users. OpenStack has a project called Keystone, which is a role-based authorization, which means that you don't just authorize people based on themselves, but also on their role. This fellow's a professor, or this fellow's an IU student, therefore has certain rights. Okay, last two of the cross-cutting monitoring. So when your job is running, you want to monitor what it's doing. You want to see problems. You want to do later studies of performance. So you want to know what went on. And there are various technologies in Ambari, Negios, Ganglia, coming from Apache and the HPC communities, which gather metrics and they produce alerts. Problem. Like when we had an when we had a corrupted file doing something dreadful on our Amazon account, obviously Amazon was monitoring that and they reported it to us. Fortunately, they were kind enough not to charge us for that disaster, that break-in, which was due to us. Actually, not our problem. It was somebody else's problem. But anyway, we implemented that problem. There's Inc as another monitoring system, which is higher level. I've already stressed the importance of infrastructure as a service, which is just not cross-cutting. So the cross-cutting is 1 through 4. 5 is infrastructure as a service, and it has all the things, including OpenStack. I put Docker, which could be in this level at the DevOps level, which is the null, because it supports the null hypervisor. And we will also use Kubernetes, which is at level 6, the DevOps also. And there are lots of infrastructures, Zen, KVM, and things like that. We discussed some of these when we discussed virtualization. DevOps, very important. Software-defined system was key to many Gartner key technologies, key emerging technologies. We have our own system called Cloud Mesh, which integrates many of them together: libcloud, Cobbler, Chef, Docker, Slurm, Ansible, Puppet, Celery. And we mentioned Docker earlier, and Kubernetes. Well, we've mentioned them many times. Interoperability, so you need standards. For services, compute, Okai is a standard from the Open Grid Forum for cloud computing. Virtualization standards and storage. CDMI is a storage standard. So getting standards approved and agreed is a bit of a fight, because people like Amazon are not terribly motivated to set standards, because it's for they don't want you to be able to move from Amazon to Google seamlessly. They want it to be painful. So you stay with Amazon because they're winning. All right, file systems is the next layer. And files will always be there because you're going to have systems in the back end, but you may not expose files. And the high-performance computing tends to, and also Windows exposes files to the user. But in most commercial data management systems, you actually expose a higher-level concept, an object, with OpenStack, Swift, or Amazon S3. And I say there's a difference between science, which tends to always use files, and commercial systems, which always use objects or higher-level system. While you're running almost certainly one or more clusters, they have to be managed. And I already mentioned Mesos, Yarn, and there's Slurm, and then we have also the systems like Moab, SunGrid Engine, OpenPBS, and Condor, which come from the Grid, what was called the Grid Initiative, which is now sort of actually grid computing died in the slough of whatever it was of despair or something. Anyway, it did not make it into the productivity slopes. And we have to worry not only about managing clusters, but also managing collections of clusters. And cluster management, scheduling, and things like that, they're all run, and the difference between planning and execution. These are sort of 4 different things, but they're all mixed up in these technologies, and they're actually mixed up in the user's mind, including my mind. But they are actually clearly distinct, and you should worry a little about that. All right, layer 10, 11, 12. And 11 has 3 components. 10 is data transport, what I already mentioned when I looked at the software stacks. The Globus line or Grid FTP is dominant in the high-performance computing community, but not so in commercially, although it is used. Most commercial systems are built around simple HTTP protocols, and also they sometimes just send things by UPS or FedEx. Well, the next set is the different data stores, which again we've sort of discussed as we've gone through already. NoSQL, SQL files, and then when we look at NoSQL, we have graphs, tables, documents, and objects. And these are all different logical structures with their own management specializations. Originally, this was all dominated by SQL databases commercially and file managers in science. Now it's much richer. Layer 12, in-memory databases and caches, object relational mappings, going back and forth between those two views, extraction tools. These are just sort of conversion tools to go from different ways of looking at things to other ways of looking at things. And it also includes it's also pretty important to keep things in memory because that's what makes things run fast. And that's an area where there's a lot of attention. It sits in the Gartner emerging technology as very important. And it's not much used in HPC, at least it is, but not by name. And it is very, very important in the big data world. Communication. Well, there's all sorts of important communications, from publish, subscribe, as you see in RabbitMQ or Kafka. MPI is point-to-point messaging, which is essentially, by definition, the fastest. You have point-to-point, which is process number 1 talking to process number 73, and you have collective, which is process number 0 sending data to all 1023 other processes. And there are various choices. It's not actually highlighted in Apache, but it ought to be. And they have different choices in functionality, performance. And performance has 2 features: bandwidth. How many bytes can you stuff down that pipe per millisecond? And also latency. How long does it start to get things tooled up and get going? Publish subscribe has got longer latency because it has queues everything. And so setting up the queue for a given message takes a little while. Where possible, you should use publish subscribe because it's got very important robustness and convenience technologies. Programming. Well, I went through how to do programming. That's that runtime. And then we have Twister, Twister2, Stratosphere, which is actually now Flink, Hadoop, Spark, so on. And then in the streaming case, we have Storm, Heron, etc. And we used to have, somewhere in A and B, you need to have either for basic programming model without streaming or one with streaming. You need to have one of those, else how can you do anything? Above that is high-level programming, and you don't have to have high-level programming. Pig is a good example of a high-level system. Shark is Spark, SQL based on Spark, and so on. Hive is SQL based on Hadoop and things like that. Drill has a SQL data interface to non-SQL data stores, including HDFS. Well, B is a little different. It's a framework as opposed to what we just discussed, and is typified by the platform as a service, which is just it's not a high-level interface. A platform as a service is a collection of tools, and that was what Google App Engine and Azure offer, and actually Amazon, of course, offers that now. 16 is the user level applications and libraries, and you'll find lots of libraries: Mahout, MLlib, MLBase for Apache. R has got a wonderful collection of libraries and statistics. Should have TensorFlow here, and the new library from Google for deep learning and other machine learning. Cafe for deep learning, ImageJ for images, lots of bioinformatics libraries, and high-performance computing as Scalapack and Petsy. Then we finally have the last layer, workflow and orchestration. That's how you join jobs together. The architecture is you have a job, which is sort of a self-contained thing which runs and has an input and an output. But then to do something real, you often need to put several jobs together because you need to, I don't know, cluster the data and then visualize it. So those are separate jobs. And orchestration or workflow does that clustering. And they have much higher, these things you're joining together are very big. They each run for a long time. So you can, workflow and orchestration is not terribly performance sensitive. And we will illustrate this with access pattern 10, which is a particular way of doing things with the 10th in this access pattern, which has workflow and orchestration in it. And you can always do this either with a sort of diagram where you stick the applications and draw lines between them to show how to link them together. That's a classic workflow GUI. Or you can sit there with your Python code and say, run job number one, then run job number 23, then number 34, take the data from 34 to send it to 63, and also to 71, and run 63 and 71, and so on. So you can do this either from a scripting interface or from a graphical interface. And the final slide from this section, which is really quite different, it illustrates single program multiple data and also a SIMD, single instruction multiple data. These are parallel computing technologies. All the parallel computing you will do, whether it's will almost always be single program multiple data and almost never single instruction multiple data, although things like graphic engines internally to the inner core might do SIMD. And it's all a question of efficiency. SIMD was used initially because if you just have one instruction engine and that instruction engine was sent to lots of different processing units, that was easier to implement than having MIMD, multiple instruction, multiple data, where each process had its own instructions. But nowadays, almost always each process has its own instructions because each process is running independently. And it's sitting there doing its own thing on its own core. But they tend to always be single program multiple data. When you do Hadoop, the maps are all running the same code. They're not producing the same answer because that same code is using different data on each process, and that data will invoke if statements in the code, and the code will be in different points at a given time. So these are just important concepts you should know about as you delve into the future of whatever big data programming on clouds. All right, that's it. That's the end of this set of notes on software.